Did you know that if semiconductor chips disappeared for just 60 seconds, the global internet would collapse, transportation would grind to a halt, and the world's financial systems would be almost completely paralyzed? This component is nearly invisible, up to 20,000 times smaller than a human hair. Yet it sits at the center of two immense forces. One powering all electronic data flows, the other serving as a focal point of sanctions in global power struggles. So have you ever wondered how trillions of chips are produced every year, and why these ultra-tiny structures can process massive amounts of data in an instant? Today, let's join Agriculture Insight to explore this entire process, where a tiny component, often called the new oil, has become something every nation strives to control. Let's get started. The rise of semiconductor chips began with the collapse of vacuum tubes, bulky, power-hungry components, paving the way for massive computers to be dramatically miniaturized. From pure silicon, humanity has built megacities within each chip. Billions of transistors, acting as microscopic switches, interconnected by metal wiring networks, stretching hundreds of kilometers across multiple stacked layers, compressing the power of entire computer systems into devices that fit in the palm of a hand. Silicon Valley, home to leading technology giants such as Intel, Apple, and Nvidia, is the birthplace and epicenter of the modern semiconductor industry. And the term silicon itself originates from the material that powered the digital age. However, the center of gravity in this trillion-dollar industry has now shifted to East Asia, where two giants, TSMC of Taiwan and Samsung Electronics, dominate nearly 70% of the global chip foundry market and almost exclusively control the production of the most advanced process nodes. In reality, semiconductors are no longer just about component manufacturing. They have become the decisive lever determining which nation will lead the AI revolution. That is why a global push to reduce dependency is unfolding at full speed. Through the CHIPS and Science Act, the United States government has committed over $50 billion to attract major companies to build fabs on American soil. Meanwhile, China, the opposing force in the trade conflict, has launched Phase 3 of the Big Fund, mobilizing more than $47 billion to achieve full self-sufficiency, from chip design to manufacturing equipment. So in your view, who will rise fastest in the global semiconductor race? Right now, let's dive deep into the most advanced high-tech factories in the world to uncover the answer within this very powerful component itself. First, every technician must follow strict sterilization procedures to protect the integrity of nanoscale microchips. In the buffer room, engineers wash their hands, dry them, and disinfect with alcohol, then put on a full-body protective suit known as a bunny suit, a special layer made from anti-static synthetic fibers. Not a single millimeter of skin is allowed to be exposed, because even a tiny amount of oil or microscopic moisture from the human body can alter the electrical properties of silicon, causing chips to malfunction or completely lose their computing capability. After completing the cleaning process, engineers step into an air shower chamber to blow away the last remaining dust particles. Everything is done with one ultimate goal: eliminating dust to the absolute minimum, because even a 1% increase in defect rates can cost manufacturers billions of dollars each year. Believe it or not, the origin of every powerful chip is quartz sand, a mineral containing up to 99% silicon dioxide, one of the most concentrated sources of silicon on the planet. But to become a semiconductor material, quartz sand must undergo an extremely rigorous refining process to extract pure silicon, followed by further chemical treatment to reach 11 nines purity, meaning that out of 1 billion silicon atoms, only a single impurity atom is allowed to exist. Once ultra-pure silicon is obtained, the next step is to shape it into a complete structure. Molten silicon is heated to temperatures exceeding 1,420 degrees Celsius in a crucible. At this stage, a seed crystal is introduced and then slowly pulled upward using the Czochralski process, forcing the atoms to align into a continuous single crystal structure. The result is cylindrical silicon ingots, each weighing hundreds of kilograms, with a perfectly uniform structure, forming the indispensable foundation of the entire semiconductor industry. From the single crystal ingot, precision mechanical processing begins to form silicon wafers. Diamond wire saw systems slice the ingot into ultra-thin discs, each less than 1 millimeter thick, thinner than a business card, yet carrying the foundation of an entire digital civilization. During this process, some material is lost in the form of silicon powder. Controlling this loss directly impacts production costs, making the optimization of every micrometer of thickness a critical economic challenge. Freshly cut wafers carry surface scratches and extremely high mechanical stress. To address this, they are sent through a double-sided grinding system to achieve perfectly uniform thickness before moving on to the initial cleaning stage. Here, the wafers are immersed in specialized chemical baths along with ultra-pure water, a solvent completely stripped of ions and impurities. Through ultrasonic vibrations and continuous rotation, the solution removes every particle smaller than 1 micrometer from the surface. At this scale, cleanliness is not just a hygiene standard. It is a physical limit that directly determines the survival rate of the electronic circuits that will be built later. From here, the wafer enters the chemical mechanical polishing stage, a critical step that brings the silicon surface to an almost perfectly flat state. Instead of rough grinding that could damage the crystal structure, the chemical mechanical planarization system uses a rotating pad combined with a specialized abrasive slurry. The process operates through two mechanisms simultaneously. Chemical reactions soften the surface, while mechanical action removes microscopic protrusions using ultrafine abrasive particles. Each layer removed is only a few nanometers thick, tightly controlled by pressure and flow sensors. After this step, the wafer is not only mirror smooth, but also achieves a level of flatness that allows insulating layers and metal interconnects to be stacked with extreme precision, a critical factor for stable electrical flow and ensuring the chip functions exactly as designed. Immediately afterward, each wafer is passed through a high-precision optical inspection system to detect defects at the nanometer scale. Only wafers that meet strict standards for flatness, cleanliness, and defect density are allowed to proceed to the next stages of microchip fabrication. As soon as they reach an ultra-clean state, the wafers are sealed inside specialized containers known as front-opening universal pods, FOUP. Precision-engineered enclosures designed to completely isolate the wafers from dust, moisture, and microscopic contaminants within the cleanroom environment. Each FOUP can hold up to 25 wafers and is made from anti-static materials, ensuring no interference with the extremely sensitive microstructures on the silicon surface. From this point on, wafers are almost never in direct contact with humans. Inside the fab, the semiconductor fabrication plant, where wafers undergo hundreds of processing steps to form billions of transistors, all transportation is handled by the Overhead Hoist Transport (OHT) system. These automated train-like carriers move along ceiling-mounted rails, functioning as a highly precise transportation network that continuously transfers thousands of FOPs per hour between processing tools. Every movement is controlled by optimization algorithms, ensuring each wafer arrives at the right place at the right time with virtually zero margin of error. Now that the foundation is complete, the wafer officially enters the most expensive and sophisticated stage of the entire process, where dozens of photolithography machines, each costing around 200 million USD, operate continuously to imprint circuit designs onto the silicon surface. Much like drawing a blueprint to build a house, an ultra-miniaturized circuit diagram is projected directly onto the wafer, precisely defining the position and structure of billions of transistors. Before that, a layer of material such as silicon dioxide is deposited onto the wafer surface, followed by a coating of photoresist, a light-sensitive material with a thickness of only a few dozen nanometers. At this stage, the photomask acts like a photographic negative, a specialized glass plate containing an NT complex circuit pattern. Then, extreme ultraviolet lithography, EUV, technology projects light with an ultra-short wavelength of 13.5 nanometers through the photomask. To generate this light, the system fires 50,000 tin droplets per second and uses lasers to turn them into plasma at temperatures reaching 500,000 degrees Fahrenheit. At such energy levels, light can no longer pass through conventional lenses and must instead be guided by mirrors polished to a precision smaller than an atom, allowing the circuit pattern to be transferred onto the wafer. From here, a complete circuit pattern, with features as small as 5 to 10 nanometers, is formed on the wafer by applying a developer solution that removes the chemically altered regions of the photoresist. After the circuit pattern is transferred onto the photoresist layer, the wafer enters the stage where the design is turned into a real physical structure. During etching, high-energy plasma precisely removes the unprotected material, forming trenches, gates, and insulating layers exactly according to the transistor design. This is essentially the shaping step of the microchip. Once the structure is defined, the wafer moves on to ion implantation to modify its electrical properties. Atoms such as boron or phosphorus are accelerated and shot into the silicon, penetrating the crystal lattice and transforming these regions into p-type or n-type semiconductors. This step determines the conductivity behavior of the transistor. Finally, the photoresist layer is removed, and thermal processing is applied to complete the formation of the ultra-small transistor structures on the wafer surface. Although the transistors have been formed, they are still just individual switches. To connect them into a system capable of processing information, the wafer enters the metal interconnection stage. Here, the Damascene process is used. Extremely tiny trenches are etched into the insulating layer, then filled with copper to create signal pathways. After filling, the surface is polished using CMP to remove excess metal and ensure perfect flatness. The wafer is then cleaned to eliminate any contaminants before moving on to the next layer. This entire cycle is not performed just once, but repeated dozens of times to build the highly complex interconnect network inside the chip. Before dicing, the wafer undergoes electrical testing using ultrafine probes to measure the signals of each chip and generate a map identifying which dies are functional and which are defective. After passing electrical testing, the wafer is transferred to the dicing stage, where it is cut into individual chips. The wafer is mounted onto a special adhesive tape for stability, then precisely cut along predefined lines using ultra-thin diamond blades, lasers, or high-pressure water jets. This process is carried out with extreme precision to ensure each chip is separated without damaging its internal structure. Water is typically used to cool the blade and wash away microscopic debris generated during cutting. Once separated, each individual chip moves on to the packaging stage. Here, the chip is mounted onto a substrate, then connected to external leads using ultrafine metal wires or advanced bumping technology. Finally, the entire structure is encapsulated in a protective material to shield it from impact, heat, and moisture. It is this packaging process that transforms microscopic circuits into complete components, ready to operate inside electronic devices. Uranium is one of the oldest elements on Earth, formed in stellar explosions billions of years before the planet itself came into existence. Yet it wasn't until 1896 that humans truly took notice. when Henri Becquerel discovered that uranium could emit invisible rays without any external source of energy. This discovery marked the beginning of nuclear physics. From tons of raw uranium ore, Marie and Pierre Curie went on to isolate two even more radioactive elements, radium and polonium, laying the foundation for our modern understanding of nuclear energy. What makes uranium remarkable is not its appearance, it looks like ordinary rock, but the immense energy it holds. In nature, about 99.3% is uranium-238, while only 0.7% is uranium-235. Yet it is this tiny fraction that can undergo fission, triggering a chain reaction and releasing enough energy to power an entire city. Because of this property, uranium is used in nuclear power plants to generate electricity for millions of people, while also serving as the core material in nuclear weapons, one of the most influential technologies in human history. From Hiroshima and Nagasaki to the nuclear arms race of the Cold War, uranium has played a critical role in shaping the global balance of power. Now, let's descend deep beneath the Earth, through dark tunnels and into a harsh, unforgiving environment, to northern Saskatchewan, Canada, one of the world's largest uranium capitals, where the journey of one of the most powerful energy sources on the planet truly begins. Uranium mining takes place far below the surface, at depths of around 450 to 500 meters, where ancient rock layers encase energy-rich ore bodies. Before reaching the ore, engineers must overcome a major challenge: high-pressure groundwater. If left uncontrolled, it can flood the site at any moment, causing tunnel collapses or halting operations entirely. To address this, they rely on an unusual method: ground freezing. Hundreds of steel pipes, often up to 200 in total, are drilled around the ore zone. A chilled solution is circulated through them at around -30 degrees Celsius, freezing both the soil and groundwater into a solid shell that stabilizes the area and prevents water intrusion. Once conditions are fully controlled, drilling begins with near-perfect precision. The drill heads are fitted with tungsten carbide buttons, nearly as hard as diamond, capable of penetrating rock formed over billions of years. The process starts with a small exploratory hole, known as a pilot hole, to pinpoint the exact location. From there, larger drills expand the access path, breaking the ore and allowing it to fall into collection chambers below. Most of the system is operated remotely, minimizing human exposure in a high-pressure radioactive environment. Even so, the challenge remains. Just a slight deviation during drilling can impact the entire operation. A single borehole can take hours, even days to complete. Once separated from the rock, the uranium ore is transported using mine carts running on rail tracks deep underground. Each train typically consists of 10 to 20 connected carts, moving slowly through narrow tunnels only a few meters wide, where light is almost non-existent. Each cart can carry several tons of ore, and the system operates nearly continuously, creating a steady flow of material from the extraction zone to collection points. Once brought to the surface, uranium ore is, in essence, just ordinary rock. The uranium itself remains locked inside, bound tightly within the mineral structure, and without breaking that structure apart, there is simply no practical way to extract it. To make that possible, the ore is gradually reduced in size through a series of crushing and grinding stages. Large chunks are first fed into industrial crushers, where they are broken down into smaller pieces, typically around 5 to 10 centimeters. From there, the material continues through additional grinding processes, each step reducing it further, down to just a few millimeters. Even then, the material is still too coarse. Inside ball mills, large rotating drums filled with heavy steel balls, the ore is continuously tumbled and ground for hours. With each impact, the particles become finer until they reach a size of about 0.1 to 0.3 millimeters, almost like fine sand. This level of refinement is necessary because uranium does not exist in isolation. It is embedded within the surrounding rock. By reducing the material to such a fine scale, the surface area increases significantly, allowing the chemical processes that follow to access and separate the uranium much more efficiently. The final step in this stage involves mixing the powdered ore with water to form a slurry, typically containing around 40 to 50% solids. In this form, the material can be pumped, moved, and processed with precision, marking the transition from raw rock to a controlled, workable feed for the next phase of extraction. Once ground and mixed into a slurry, the uranium ore enters the extraction stage. The mixture is transferred into large tanks, where sulfuric acid is added to dissolve the uranium. This process takes place under controlled conditions and typically lasts several hours, with continuous agitation to ensure even contact. Rather than breaking down all the material, the acid selectively targets the uranium, allowing it to dissolve into the liquid, while most of the surrounding rock and minerals remain in solid form. Once the reaction is complete, the mixture separates into two distinct parts: solid residue and a uranium-rich solution, which can contain up to 80 to 90% of the original uranium content. This solution is then collected, becoming the primary feed for the next stages of refining. Once uranium is in solution, the next step is to recover it in solid form. Heat and chemicals are carefully controlled to remove excess water, allowing uranium to crystallize into tiny particles that settle at the bottom over several hours. The resulting material is then dried into a yellow-brown powder known as yellow cake. Its color comes from uranium oxide, making it stable and easier to transport. A single 200-liter steel drum can contain enough uranium to be further processed into fuel. Although it looks quite ordinary, yellow cake is a globally traded material used by uranium enrichment facilities. And unlike what movies suggest, it does not glow. Just a simple yellow powder that holds an immense amount of energy. After being concentrated into yellow cake, uranium is still not ready for use. In its solid form, it isn't suitable for the next critical step, enrichment. To make that possible, it must be transformed into an entirely different state, a gas. To do this, yellow cake undergoes a series of chemical reactions, converting it into a compound known as uranium hexafluoride, UFC. What makes this substance unique is that it can turn into a gas at a relatively low temperature, around 56 degrees. This property allows uranium to be fed into enrichment systems, where even the smallest differences between isotopes can be precisely separated. At this stage, the process is no longer about handling material. It becomes a matter of fine-tuning at the atomic level. In nature, uranium is almost unusable. Only about 0.7% of it is U-235, the isotope capable of sustaining a nuclear reaction. That fraction is so small that, without intervention, the entire mass of uranium holds very little practical energy value. That's why facilities rely on specialized machines known as centrifuges. Inside them, uranium gas is spun at speeds of up to 50,000 revolutions per minute, fast enough to create forces capable of separating incredibly small differences in mass. The heavier uranium is pushed outward, while the lighter portion, U-235, moves closer to the center. This process is repeated across hundreds of stages, each making only a tiny adjustment, but together producing a significant effect. After many such cycles, the concentration of U-235 is increased to around 3 to 5 cent, just enough for the uranium to truly come alive and be used as fuel in nuclear reactors. After enrichment, uranium is no longer kept in its gaseous form. The UF gas is cooled and converted back into a solid, then undergoes further chemical reactions to become uranium dioxide, UO2, a more stable form suitable for fuel fabrication. At this stage, uranium begins to take shape again as a fine black powder. From a nearly invisible gas, it is transformed into a material that can be handled, processed, and precisely controlled. These powder particles are then tested for purity and size to ensure uniformity before moving on to the next stage. From this seemingly simple powder, uranium will be pressed and shaped into fuel, a small change in form, but a major step in its practical use. From a fine powder, uranium dioxide is pressed under high pressure into small pellets, each only a few millimeters in size, resembling simple tablets. Despite their size, each pellet contains a remarkable amount of energy. These pellets are then placed into furnaces and heated to around 1600 degrees Celsius. This process, known as sintering, removes internal pores and increases density. Under such extreme heat, the uranium dioxide particles bond tightly together, forming a solid structure. The result is a fuel pellet with ceramic-like hardness, highly durable, heat-resistant, and stable enough to operate inside a nuclear reactor for years. From a fine powder, uranium has now been shaped into a compact and reliable form, ready for the next stage of assembly and use. Once formed into fuel pellets, they cannot be used immediately, and must be assembled into a complete structure. Each pellet is stacked in sequence inside zirconium tubes, a special metal that can withstand high temperatures and does not interfere with the nuclear reaction. Once the tubes are filled, both ends are sealed, forming fuel rods. Each rod contains dozens of pellets aligned in a straight line, designed to operate reliably under extreme temperature and pressure conditions. After the fuel rods are completed, they are not used individually but are assembled into fuel bundles. Each bundle typically consists of around 30 to 40 rods, most commonly 37, arranged in parallel and secured by a metal frame to maintain precise spacing between each rod. But the journey doesn't end here. Have you ever wondered how electricity and other forms of energy are generated from these uranium fuel bundles? Once the fuel bundles are fully assembled, they are placed into the reactor core, where the entire energy transformation process takes place. Here, uranium atoms begin to undergo fission. When an atom splits, it releases heat and neutrons, which in turn trigger further reactions. This creates a continuous chain reaction, generating an immense amount of heat. Inside a reactor, temperatures can reach around 300 degrees Celsius, enough to boil water and produce high-pressure steam. This steam drives turbines spinning at thousands of revolutions per minute, powering generators and producing a steady flow of electricity. A single reactor can supply power to hundreds of thousands to millions of homes, all originating from reactions occurring at the atomic level. After a period of operation, the fuel inside the reactor gradually becomes less effective and is removed. Although it no longer generates energy, it remains extremely hot and radioactive, so it is placed in deep cooling pools, where the water both absorbs heat and acts as a protective shield. These fuel bundles can remain in the pool for years, even decades, before being transferred to long-term storage systems. At this point, many people wonder, what would happen if someone fell into one of these pools? And could the water be safe to drink? The answer is that the water in these pools is actually highly filtered and strictly controlled, making it technically very clean. But don't rush to drink it. The real danger isn't the water, but the fuel rods below. If you get too close, the radiation can damage cells, cause radiation burns, and affect internal organs. So while the water may look clear and harmless, this remains one of the most tightly controlled environments in the entire nuclear industry. In the United States, 7 out of every 10 women receive a diamond engagement ring when they are proposed to. In China, that figure has already reached 50% in major urban centers, a tradition that, in reality, was only introduced less than a century ago. Before that, diamonds were neither rare nor symbols of love. The turning point came when De Beers implemented a strategy to control the global supply, manufacturing scarcity and spreading a message that would shape an entire century. A diamond is forever. Since then, millions of diamonds have been frozen inside jewelry boxes, gradually becoming a widely accepted measure of a man's commitment and sincerity. But that power is only relative. From a physical standpoint, diamonds can burn at temperatures of around 760 degrees Celsius. And in the marketplace, nature's monopoly is now being challenged by technology. Lab-grown diamonds can be created in just a few weeks, match the quality of mined stones, and cost up to 70% less. Russia still holds the largest diamond reserves on the planet. Yet Pink Star, the most expensive diamond ever sold at auction, is owned by a Hong Kong billionaire. And you, if you had $72 million in hand, would you choose this symbol of power or trade it for half a ton of pure gold? Right now, we take you to Diavik, one of the few diamond mines in the world located beneath the frozen waters of the Arctic. Amid temperatures plunging to -30 degrees Celsius and relentless storms, this site stands as both an engineering marvel and a convergence point for diamond-bearing ore bodies formed 150 kilometers deep within the Earth, under temperatures of around 1,000 degrees and pressures reaching 50,000 atmospheres. After billions of years in the mantle, only a small fraction of these diamonds were carried to the surface by ancient volcanic eruptions, becoming trapped in kimberlite rock, the very target of mining projects worth hundreds of millions of dollars, where humans challenge nature itself to lay their hands on these hidden treasures. Diamond mining begins with high-precision geological exploration. Satellite imagery, gravity sensors, magnetic surveys, and indicator minerals such as garnet and ilmenite are used to trace kimberlite pipes hidden deep underground. But the odds are brutally low. Out of every 1,000 structures identified, fewer than 1% contain sufficient reserves to become a commercial mine. In the world of diamond mining, everything begins with an explosion. Once a site is confirmed, extraction proceeds using one of two main methods, depending on the depth of the ore. At open pit mines, massive spiral-shaped pits are carved into the ground, some stretching up to 1 kilometer wide and plunging more than 500 meters deep. Mining here follows a strict cycle. First, drilling rigs bore hundreds of blast holes, each with carefully calculated depth and angle according to engineering design. These holes are then loaded with bulk explosives, most commonly ANFO, a mixture of ammonium nitrate and fuel oil, chosen for its powerful blasting capacity and relatively low cost. The charges are detonated remotely using delayed blasting techniques. This method must not only fracture the rock, but also precisely control ground vibrations to protect pit walls and prevent diamonds inside the rock from cracking. Immediately after the blast, tens of thousands of tons of broken rock are loaded onto ultra-class haul trucks, machines as tall as two-story buildings, capable of carrying up to 450 tons per load, and transported to the surface. For deeper deposits, underground mining methods are employed. Instead of excavating from above, engineers construct a network of tunnels beneath the ore body, then blast the lower sections, allowing the entire rock mass to collapse under gravity. Workers and machinery operate in narrow tunnels, extending from 700 to more than 1,000 meters below the surface. These are extremely harsh environments, where rock temperatures can reach 40 degrees Celsius, requiring massive ventilation and cooling systems to continuously pump fresh air down from above. But deep underground, danger is always close at hand. In 2017, the Mir diamond mine was struck by disaster when water from an overlying lake suddenly flooded in, breaching protective barriers within seconds and leaving the world's second-largest diamond mine paralyzed for years. Despite all these immense efforts, diamond mining efficiency remains astonishingly low. On average, more than 250 tons of earth and rock must be excavated, transported, and crushed to recover just a single carat of diamond, barely larger than the tip of a pencil. Once brought up from deep underground, tens of thousands of tons of kimberlite ore are hauled by heavy trucks directly to centralized processing plants. It is here that the rock enters a vast automated system, marking the beginning of the process of extracting its most valuable crystals. Massive crushing machines, each weighing dozens of tons, play a central role in breaking down large blocks of ore. Operating like steel jaws, they are powerful enough to crush even granite. Yet despite their absolute hardness, diamonds are extremely brittle. A misdirected impact can shatter a crystal structure into fragments, completely destroying its commercial value. For this reason, crushing forces must be calculated with extreme precision. Strong enough to break the surrounding rock, yet gentle enough to protect the crystals within. The process is carried out in multiple stages, beginning with slow compression using heavy roller presses, followed by roller crushers, and concluding with vibratory separation to maximize recovery efficiency while minimizing risk to the gemstones. After crushing, all fragmented material moves into the cleaning stage, where clay, mud, and fine dust are removed from the ore. If not thoroughly eliminated, these binding materials can clog machinery and interfere with modern separation systems. Industrial washing units use large rotating drums, multi-deck vibrating screens, and high-pressure water jets to create turbulent flows that scrub the material clean. At this stage, particles smaller than 1 millimeter are completely screened out, as their likelihood of containing diamonds is extremely low relative to the cost of processing. But for commercial-grade diamonds, the journey is only halfway complete. Their true value is unlocked inside the cutting workshop, where each rough stone is examined, evaluated, and cut with absolute precision to become a gem of near-perfect brilliance and balance. Every diamond is entirely unique. No two stones are ever exactly the same. That is why, before cutting begins, specialists perform a full 3D scan of each rough diamond to analyze its shape, internal flaws, clarity, and the way it reflects light. This data is then fed into specialized software to calculate the most efficient and valuable cutting options. Some diamonds are divided into multiple smaller stones to maximize profit, especially when internal imperfections make crafting a single large gem less viable. Others, particularly rare or exceptionally clear stones, may be kept intact to create a one-of-a-kind piece. Every decision at this stage is driven by a single goal: to unlock the diamond's full potential by balancing brilliance, symmetry, color, and weight. The aim is to produce a stone that sparkles with maximum intensity, displays optimal color, and retains as much mass as possible, while honoring the natural beauty that took billions of years to form. Once the evaluation and planning stages are complete, the rough diamond enters its most critical phase: cutting and polishing. The process begins with preliminary cutting using high-power lasers, accurate to within 0.001 millimeters. The laser targets the stone's weakest structural points, allowing it to be shaped or divided without causing unintended fractures. This is followed by manual grinding and polishing. Master craftsmen use polishing wheels coated with diamond dust, because only diamond is hard enough to shape itself. Throughout this stage, pressure, contact angle, and rotational speed must be constantly adjusted to ensure each facet meets precise geometric proportions. The entire process typically takes between 3 and 8 weeks, depending on the stone's complexity. The final result is a flawless structure, with facets engineered to reflect light at maximum intensity, creating the distinctive brilliance that defines a diamond. Once its shape is complete, a diamond is not released to the market immediately. It must first undergo a rigorous grading process at specialized laboratories. Here, the stone is examined under advanced microscopes to assess 4 core criteria: color, clarity, carat weight, and cut quality. Even microscopic carbon specks or ultrafine surface blemishes are recorded, as they ultimately determine the diamond's final commercial value. If the stone meets these strict standards, it receives a unique digital signature, a laser-engraved identification code etched directly onto its outer edge. Invisible to the naked eye and readable only under high-magnification microscopes or loupes, this code serves as a critical key for traceability and absolute transparency. Finally, trusted institutions such as the GIA issue an official digital certificate, a comprehensive identity record permanently stored within a global system. In essence, this certificate is the diamond's passport, verifying its quality and safeguarding its value on the international market. Once certified, a diamond enters its final stage, becoming the centerpiece of a global jewelry market worth more than $300 billion each year. At major houses such as Cartier and Tiffany & Co., craftsmanship demands absolute precision, from casting and setting to meticulous hand finishing. To maximize light performance, artisans favor techniques like hidden settings or pave mounting, minimizing the amount of metal that obscures the stone's surface. The goal is to secure the diamond firmly while allowing light to pass through and refract from every possible angle. The result of this uncompromising process is a product with near eternal durability. In reality, gold can be scratched, melted, or worn down by mechanical stress over time, but a natural diamond cannot be destroyed by such ordinary forces. That is why a diamond worn by a bride on her wedding day can remain perfectly intact, even when passed down through dozens of generations. Although the pine family includes more than 120 species, only a small fraction is exploited industrially in 3 main directions: resin pines used for engineering materials, nut-producing pines that yield high-value fatty seeds, and Christmas pines, trees cultivated primarily for the holiday season and rarely involved in modern industrial supply chains. Yet beyond their economic value, pine trees possess a survival mechanism that continues to astonish scientists. Many species not only survive wildfires, they actually depend on fire to regenerate. Extreme heat causes pine cones to snap open, releasing seeds onto mineral-rich ash, where a new generation can take root. This very mechanism is why forestry authorities in the United States and Canada practice controlled burns, simultaneously triggering natural regeneration and reducing the risk of catastrophic wildfires. And fire is not the only force pine trees have learned to defy. Time itself is another. In California's White Mountains, the Methuselah pine, a bristlecone pine, has lived for more than 400 to 800 years. Long before the Egyptian pyramids were built, it had already taken root on barren, rocky slopes, enduring to this day as one of the oldest living witnesses in human history. Across the vast industrial pine plantations spanning hundreds of thousands of hectares in the southeastern United States, the resin harvesting season runs steadily for 8 months each year, a rhythm that has remained nearly unchanged for centuries. The process begins with the selective scraping of the outer bark to create a stable surface for subsequent operations. Workers then use a resin axe, a specialized tool with a square head and beveled blade designed specifically for opening resin channels, to make a slanted cut about 4 millimeters deep, just enough to reach the resin-conducting layer beneath the bark. This precise depth triggers the tree's natural defense mechanism, forcing resin outward to seal the wound while preserving the structural strength of the wood core. Next, the flat side of the axe is used to form a horizontal lip, a guiding edge that secures the collection spout and directs the resin along a controlled path. As soon as the groove and guide are formed, milky white resin begins to seep out under internal pressure, traveling along the grain of the trunk and flowing downward by gravity. In the initial stage, the resin is collected in open cups to monitor flow rate and minimize contaminants. Once the flow stabilizes, the system transitions to collection bags pressed closely against the trunk, reducing air exposure and controlling oxidation before the resin is sent for distillation. Every 5 days, the cut surface is delicately refreshed to maintain resin pressure without exhausting the tree. With this approach, each pine yields an average of only about 3 kilograms of resin per year, yet it can be tapped continuously for decades. At the scale of millions of trees, precision in every small cut has transformed pine resin into a renewable annual resource, rather than one extracted at the cost of forest decline. And now, we arrive at the main character of today's story, the raw material behind those golden drops of pine oil. In traditional pine forests, pine nuts are still harvested entirely by hand. When cones have fully matured and dried naturally, they detach from the branches and fall to the forest floor, turning the woods into a scattered trove of riches. Harvesters walk through the forest, picking up dry cones from the ground and selecting only those that remain intact, free from moisture damage or insect infestation. This is a slow method, but one that preserves the full quality of the seeds inside. For cones that have not yet fallen, harvesters must climb the trees themselves and handpick them directly from the branches. The work demands experience and precision, as pine trunks are tall, slick, and sparsely branched. Each cone is gently twisted off to avoid injuring the branch, ensuring the tree can continue producing cones in future seasons. Each hectare of wild forest yields only about 400 kilograms of cones, equivalent to roughly 60 kilograms of raw seeds, and this output can fluctuate significantly under harsh weather conditions. In return, pine nuts accumulate an oil content of up to 60 to 70%, rich in unsaturated fatty acids, a nutritional profile that gives them exceptional value. Meanwhile, in large-scale, cultivated pine plantations, the key to dramatically higher productivity lies in mechanized harvesting systems. Trunk shakers equipped with hydraulic gripping arms clamp firmly around the lignified trunk, transmitting precisely calibrated vibrations into the canopy. This causes cones that have reached physiological maturity to fall simultaneously, allowing entire plantation blocks to be harvested in just a few days. However, full mechanization is limited for younger trees or plots undergoing genetic improvement. In these cases, harvesting crews rely on lift platforms with reaches of up to 20 meters to access the upper canopy, combined with ground workers using long poles, approximately 9 meters in length, to selectively dislodge cone-bearing branches. While this approach delivers lower yields, it offers superior control over seed quality and preserves the tree's long-term growth structure. Yet harvesting is only half the story. The true value of pine begins to emerge when resin and seeds reach the factory, where even minutes of delay can lead to resin oxidation or a decline in oil quality within the kernels. At gum rosin production facilities, each batch of 20 to 50 tons of raw pine resin is fed into heated tanks to soften the material and reduce its viscosity, transforming it from a thick, sticky mass into a uniform liquid ready for further processing. From there, the pine resin is directed into distillation towers, where it is heated to temperatures of approximately 155 to 170 degrees Celsius. The lighter fraction with a lower boiling point, pine essential oil, vaporizes first, then is condensed and collected as turpentine. The non-volatile residue that remains is resin-rich in resin acids, the direct precursor to gum rosin. After distillation, the molten rosin is spread into thin layers and gradually cooled using water or forced air. This controlled, slow cooling process preserves the stable amber yellow color and minimizes brittleness or cracking between production batches. Once fully solidified, the gum rosin is cut into dense solid blocks weighing approximately 20 to 25 kilograms. These blocks are then graded based on clarity, color, and mechanical properties. From this point, lighter, acid-stable grades are directed into packaging adhesives and printing inks, while darker grades are allocated to rubber compounding, coatings, and heavy industrial materials.